Esto es la camisa.
Okay.
No te pase las 10:45.
Okay. Okay, I'm going to be a little bit more conservative than Dave. All we did is running some sensitivity tests for WRF and some setup experiments, some configuration that James and James and Chris gave us. So first, what we did, we ran 18 different simulations for 36 hours each for July 15 and 16. During this time of measurements that they made in 2013, using Mocker's monsoon experiment settings. Using these settings are 3 domains with spatial resolution of 30, 10, and 2.5 kilometers, 28 vertical levels using a Yonsei University boundary layer scheme, very simple microphysics scheme like the warp single moment with 6 hydrometers, using the shortwave radiation Goddard and no LSM for surface physics, and no cumulus in the inner domain. So we run 18 different sensitive tests. First, in the other simulation I did in Mexico City, I saw that we can get an added value using 1 kilometer, but Chris said that the best you can get is at 2.5 kilometers. So now I agree with him, but let's see the results. Then I tried 2 different boundary conditions from 2 reanalyses, one from NAR and another from ERA interim. Then I added more higher resolution I did some simulations with 50 levels and another with 100 levels. I used another land use data that is MODIS for 30 seconds. The other land use, land cover that I use is the defaulting WRF. The USGS for Mexico is 1993. Then I changed to another shortwave radiation scheme. Then I tried using SST update during simulation, not only and as an initial condition, but that's something that every time that the boundary conditions are updated, the SST is updated. I tried using NOMP just to change from NOAA land surface model. That NOMP has dynamic vegetations and another specifications from of the surface that I didn't change anything, only dynamic vegetation. I tried adding a 14 days spin-up time to see if the model, how the model behaves. And with this spin-up time, I added in some simulations analysis nudging. Everything is only qualitative. I just compared plots. This is only to try to iterate to a good configuration to run the whole period of observations in 2013. So anything can change, and you can give me your input, and anything you see that is not very right. Okay, these are the 18 simulations. I'm not going to explain all the table. I'm just going to, the green simulations are the one that I'm going to show you today. This is the base case, the Mocker-Castro test. This is with MODIS. That is the kind of the best for me, at least. This is another simulation with everything that I tried, 14-day spin-up, 50 levels in vertical, and all that stuff. This Sims 17 is the base case, but using ERA interim. And 16 is the same as 14, but using ERA interim. Okay. As I said before, I tried to do a higher resolution. Well, this is the experiment that Dave ran and all of you ran in 2013. I used the two stations only, one in Onabas and the other is Chihuahua. I tried doing this for domain, but it didn't work at all. So I'm not going to show you anything about it. Okay, so this is just to put in context where the stations are. This is one. Onabas is to the Gulf of California, and Chihuahua is to the other side, the mountain. Here's a big mountain here. Okay, so this is the first case with a Mokers-Castro setup, just as a base case. So we can see that there is a big overestimation of temperatures. See, I mean, this is T2 compared to the measured temperature on surface. This is water mixing ratio at surface. This is precipitation. And this is precipitable water integrated in the vertical to compare with the measurements that David have done in 2013. We can see that there is a lot of overestimation of temperature to the side of the Gulf of California, but very good performance to the other side of the mountain. We can see too that the model is dry to the side of the Gulf of California, and to the other side the performance is good enough. But when we see precipitation, we see a lot of precipitation in the side of the Gulf of California, when more than 5 millimeters per hour, when there is only about 1 millimeter. In precipitable water, there is a kind of good performance. Now that Dave said that it is about 2 or 3 millimeters, Dave?
In Onabas?
No, the error.
Oh yeah, 2 millimeters.
So this is not that bad with this uncertainty. Plus less. Yeah, but there is not 1 centimeter here. This is 2 or maybe 4 millimeters. So, well, then talking with Chris, he said that maybe one thing could be the SST update, and we thought that this could be with the land use data we were using that was very old. So then we changed to MODIS, that is from 2001, added 50 vertical levels, and this gave a lot of better results, at least in precipitation and precipitable water. We still the Onabas side still being very high in temperature. We still being the Onabas side still being very dry compared to the water mixing ratio in surface, but in rain it's at least the magnitude is right, and the precipitable water it's still good enough. Okay, then I tried the spin-up, I tried SST update, I tried analysis nudging, and yes.
Can you explain what were the differences in land use?
Okay. I haven't looked at it in detail, but all I can tell you right now is that it's newer. This MODIS is from 2001, and the other is. This is the same resolution, 30 arc seconds. But right now I can't remember exactly what.
It's a different land use.
Yeah, it's a different land use classification. Yeah, it's different. It's a different classification.
So the default land use is the USGS.
Yes.
Is 1 year on the code, and the new modus land use is average of.
But the new is the 50 arc seconds, right? The 15 arc seconds.
From satellite product.
Yes, MODIS, yeah. But the 30 arc seconds is from 2001. The newer, the 15 arc seconds is the climatology, right? I mean, is that composite from a lot of years?
No.
average of 7.
Yeah, no, but she's saying that there is another that is an average of a lot of years, right? I thought that that was 15 arc seconds. There's two models.
They all have like 2 minutes, 30 seconds.
Yeah, but that's USGS. Okay. I haven't seen that. Sure. Okay. So this is with this tube date and still NAR. And even when we get a closer trend in water mixing ratio and a closer maxima in surface temperature, we get a lot of precipitation that is not there. Even when we get a better precipitable water trend. So this, until now, we see that the surface is playing a big role here. Okay, now we are going to era interim.
Sorry, Carlos, can
Yes.
you go back on that one?
Sure.
So, okay, all right, let's see. It doesn't even look like you have convergence or anything. You have that really big peak.
Yeah, well, that's just right here.
Maybe. Okay.
Yeah, maybe. Yeah. Okay, now I changed and I forced with era interim. And this is the base case, just forced with era interim. We have in temperature, we have a lot of better performance. The same in water mixing ratio, but in rain, is a lot. This overestimating is generating a lot of rain where there is no rain. Talking with David, he said that this peak here is too big. It's almost like it in the wall column. There's a lot of vapor. So, well, he said this is not realistic. So we are trying to understand why is this occurring, just changing the boundary conditions. Then I did the same thing, but with air interim, with all the increased vertical resolution, analysis nudging, analysis tube date, and this did not get any better. We get a lot of precipitation where there is nothing, even when precipitable water is kind of better. But mixing ratio and surface is a lot of more than we would expect. Except,
Can you go back?
sure.
What are the values there on precipitation?
Yeah.
It's off the chart.
These ones should be, these were like 20 millimeters, something like that. It was very high. That's why I cut it, because otherwise you wouldn't see the measured peak. Well, since David said that this is what was very anomalous, we tried to do some vertical profiles to examine what was going on. So I'm showing you again. This is precipitation from base case with NAR, precipitation from base case with era interim, and precipitation with NAR and MODIS. Here's the peak. This is about the 197.1 Julian day. So I took the vertical profile at that point, and this is what I got now. We see that since integrated water vapor is in the wall column, if you can see the blue line, here is a big area that is not here or here. So there is not a lot of water vapor in the surface, so everything is in the column. But until now, we don't know really what is happening. The next thing that we did was to looking at the first layer of the surface, and we saw that with the era interim is the black one, NAR with base case is a blue line, and NAR with MODIS is a red line. So we can see that era interim in general is a lot of moist than the NAR. So maybe that's one probably reason why we are getting a lot of water in the atmosphere.
Did you use the wrap for the soil moisture, or did you take that out?
No.
So did you
Yeah, I just got from ERA interim and from NAR.
were you able to compare it? Because we use that too, because it had better fields than the actual.
The rack,
The wrap?
drop, yeah. I remember that, yeah. I didn't try it.
Okay.
Yes.
Carlos, I want to say before I give my comment, we have a conference call at 10:30 I have to go to, so I'm going to have to go after I give my comment. But I stayed because this is something obviously I've been involved in, and I'm very interested in these kinds of results. But I think from my point of view, the take-home conclusions we're getting from this is there's very high sensitivity to the specification
Yes.
of the forcing data.
Yes.
There's very high sensitivity to the specification of the surface boundary conditions.
Yes.
In terms of the land cover types and the specification of the initial soil moisture.
Yes.
I think this actually makes a very strong argument to see what happens when we can use better sources of soil moisture data to specify the initial conditions. We talked about this yesterday
Yeah.
in Carlos's talk.
Yeah, with this map
With
stuff.
this map. And then the other thing is that this really motivates the use of GPS water vapor
Yes.
to constrain the initial and boundary conditions of the water vapor.
Yeah.
Because it's clear that there's such a high sensitivity to how you initialize this and how that's realized into the integrated model of three-dimensional fields.
Yes.
So I guess before I leave, I just want to make sure you agree with what I'm saying.
Yeah, sure. No, I totally agree with you. We need to get a soil moisture better and try to get there is another ERA interim set that they say is better. So if we can get some data just to run some tests, that would be great. And well, that's all I want to show you. So keep.
Anyone has more questions?
First one.
Just adding to the comment of Chris, it's maybe not only soil moisture, but also the fluxes, the evapotranspiration, because there's always some vegetation between the soil and the atmosphere. So I think that's also some part where we should work on, so to get the fluxes from the surface right.
Yeah.
And what I noticed, the event you study over here is like a real small rain event, in my opinion.
Yes.
So maybe it was just a very local conviction, and maybe you should do the exercise for a more a bigger storm that covers a larger area.
Yeah, rain is one of the things that the model struggles to get right. So that's why I didn't try to replicate another case with a lot of more rain. It's just some rain to see if there is happened something.
Yeah, I think one of the things that you could do also, I'm sure you're going to do it, is just develop your climatologies for the stations and calculate the statistics on them, coming up with things like timescales, coming up with distributions, statistical distributions, and compare those to the observations.
Oh, yeah, all this is only to iterate to a kind of better configuration for running the
No, I understand, but I want to bring back to the idea of, for example, if you looked at your, are you getting your convergence correct. So it's not just the maximum value. Are you getting the time, like, again, I just harped on for the last 30 minutes. Are you getting the time scale right? Run statistics on that and see if you can replicate the actual time scales, because that tells you something about the convergence, an actual physical process. Okay, that the model has to get right.
Okay.
Okay. Any more questions? Well, we thank Carlos.
Thank you.